Very well. Hello, everybody. Let's start. So today we have again one interesting topic to discuss, which is about naive Bayes. This is a new, somehow different type of machine learning models. And for some very specific reason, I choose to discuss about this because it gives a different perspective toward another type of ML technique that I hope you learn about. Specifically, the foundation of naive Bayes is Bayes nets, which we discussed extensively in the AI class 580. But for this lecture today, you definitely do not need the key concepts in Bayes net. Hopefully, if you have this intuition, that would help you to understand this a lot better, but it's definitely not necessary. And if you have any question about that, please let me know. I'm happy to explain. So before we start, do you have any question for me? I hope you can hear me well. Very well. Okay. Let me see. Let me turn this off. This is better. So difference between the type of model that we discussed so far, especially about perceptron, is mainly about the type of model that we have. So both of these models, both perceptron, neural network, and deep neural networks, as well as these naive Bayes models, you can consider them as some sort of classifiers. So you have some classes, you have data, and you want to build some model that give you some prediction over the labels that you have. So the very same procedure, nothing new except the internals of the model. And this internals boils down to the type of structure that we have in naive Bayes, which makes it interesting and makes it, and that's why I choose it specifically to talk about it. Because again, this is very much different from something like neural network or perceptron. In perceptron, you remember you had some feature value. So this was a vector. You represent it by f of x. X was your input. Okay. And then you had some activations, right? You had some activations, ZIs, which you calculated based on these feature vectors, right? And based on this ZI, once you activate them, then this provided some sort of reasonable value based on which you could decide what is the right label for the specific inputs that you have. Okay. And then we looked at it and realized that if we could somehow turn these activations to some probabilities, this gives you a much better framework to reason about, right? We discussed that if we only have these activations, this would not be sufficient for us to distinguish between different classification, specifically when we have some specific reason why we prefer one decision boundary over another type of decision boundary. So we talk about transforming these to some probabilities. Here, we want to turn the focus whether we can really make the whole model, including these feature values, probabilistic. So instead of just changing the output to some probabilities that we could reason about, can we make the whole thing here something probabilistic that we could reason about the whole thing, right? So if we have some probability, since these are feature values, like what we can do with these feature values, there are some numbers we cannot really reason about. So if we change our input, these values would be totally different. So we cannot rely on these specific values, and we cannot do any probabilistic reasoning based on these values. So, and that's why, and that's the key reason why you hear this discussion that why some models like neural networks are just black box, because you cannot peek inside. If you can look at these values doesn't mean anything to you, right? And for deeper network, you saw that like you have different layers, right, all the way down to inputs, your inputs. Each of these layers were a bunch of neurons and give you some activations, which could be from -infinity to +infinity. So you cannot really do anything with these values. These are just simply some values. But if you have some probabilistic models, you know that with principles that you know from probabilities, you can reason about the structure of the model. You can do some changes structurally. You can learn some parameters for the model, right? And you can also learn some hidden concepts, right? So these probabilities are interesting in a sense that gives you some intuition what it means and what model has learned from the data in a probabilistic sense. The internal of model, you can reason about the internal of model, not just the output of the model. Does it make sense? Because this is important to distinguish, and I hope that you see the reason why I picked this naive base to discuss today, and what is the key reason behind this. Do you have any question about that? And this type of models are called, as you see from this discussion, is called model-based, right? So we have a particular model, a probabilistic model, probably a better name is probabilistic model is a better name for this type of classifiers. Because the whole thing, the whole model is probabilistic. For deep neural network, we could not say that. The internal of the model are just activation, they're not probabilities. So again, the same sort of classification, as you know, so I'm not going to talk about the detail because we discussed it extensively. This could be a sort of email that you get from text. So you look at the text, you extract some features, right? Some patterns from the data, and your model find these patterns from the data, exploit the feature values, and learn from the data how this looks like, and decide whether the text could be associated to a spam or ham, or benign, you could say. So it's typical classification problem. Or could be a kind of digit recognition where the only difference is that you have more labels. You have labels from 0 to 9, and based on the feature that you have, typically in features in for digit classification are basically the raw features in the image, whether a pixel value is 0 or 1. For this black and white digits, you could reason only based on 0, 1, but for color-based, you have like 3 channels and you have values from 0 to 256, right? So there are some differences, but essentially you're talking about feature value or even some high-level features like the number of components that you have, the aspect ratio, number of loops that you have, and so on. So these are some high-level features besides these raw features that you can expect from your data. And these high-level features are also extractable from data. Like you can look at the image and you can see, okay, how many loops it has? It has 1. How many loops it has? 0, right? So these are some high-level features that you can extract from the data. And then you can decide about the label, the true label. And you have some other type of classification, like for medical diagnosis, right? You want to look at the image and see whether this image is about the cancer tissues, the human tissues, and then whether you want to identify whether it is cancerous or not. For fraud detection, you want to look at the account activities, and based on the activities, you want to associate whether there is some fraud going on or not. For essay grading is the same. For customer service email routing is also the same. So these days, so many of these tasks, which was impossible to think about it as a sort of ML task, now it's really possible to recognize them and do them as a classification task, right? And classification, again, you know that is not the only type of machine learning task, but by far the most popular one. So let's jump into the model-based classification. Again, we want to build a model, some sort of Bayes nets, where in Bayes net, we have nodes and connection between nodes. So we have a bunch of nodes and nodes are connected, right? And these nodes are probabilities, right? Or either probabilities or conditional probabilities, and then we could reason about the joint distribution of all of these variables. And the connection is the dependence between two variables. So for example, this variable, if this is like y and this is x, y is dependent on x. This dependence could be just correlation or could be causation, but there are some dependence, so we cannot. So in Bayes net, you know that if we have this connection, this means that x and y are not dependent. So if x and y are dependent, independent, this means that the probabilities for the values that can be assigned to each of these variables are not really dependent on what value is assigned to each other variables, right? So and this gives us some flexibility, you know, that by probability, if we want to calculate the joint probability of x and y, by default, we know that for maintaining this probability of x and y, this is joint probability distribution, we require a table of like a large table that consider all combination of the values between x and y. So this is a large probability tables. But if we assume that these x and y are dependent, so if the model looks like this is x and y, and there is no connection between them, we can calculate this very easily. We can calculate this p of x multiplied by p of y. And basically for calculating this joint probability, we do not need such large table. We only need to maintain a small table for x and y. And then whoever asked about this joint probability, we could look at different rows in each table and calculate this joint probability. And that was the key power beyond a model like BaseNet that enable us to reason about this joint probability, and the whole power beyond these model-based approaches is this kind of reasoning that we could do based on mathematics behind this, right? Do you have any question about this? But this is really the only thing I assume you need to know about BaseNet. The rest, there are some details, obviously. We talk about like much more detail in the AI course, but for Naïve base, this is pretty much what you need to know. And then now for this is that you need to decide about the structure of the model and as well as the parameters that you need to consider for this model. So these two challenges are what you want to learn for this type of model-based classification. By a structure, we mean that what are these? What is the label? How these are connected? And so on. And parameters means that what is the probability distribution of each of these variables, right? These are pretty much what you need to know. So a structure plus parameters. This is what you can call model-based learning. Let me see, I can see some noises here.
Yeah, it sounds like some feedback.
Is it better now?
Yeah, well.
How about now?
Yeah, it seems to be.
Is there still the feedback?
Yeah, it seems to be coming in
hearing
intermittently. Maybe your microphone is too close to your speakers.
Let me move it there. That's strange. I hope it's not too bad. Is it?
Yeah, it's not great.
Yeah, it's like a mosquito hovering in my ear.
Sorry about that.
Do you have headphones maybe? That would probably solve it.
Yeah, I can put my headphone. How's it now?
Not hearing anything, so it sounds pretty good.
Yeah, it sounds great.
But I can hear myself. That's the problem.
Maybe just switch back for the moment, I guess. It seemed kind of intermittent, and maybe it wasn't going on like, I don't know, when you last, right before you put in the headphones. So
Can you hear me?
yep.
Yeah.
Is it better?
Yeah.
Okay, let's do it that way. Okay, at least, yeah. Let me know wherever the voice comes back.
No, it
So
sounds great.
yeah, thanks. So yes, so this is about the model-based approach, right? So we want to learn this structure and the parameters of the model, and this is pretty much what we need to know for naive Bayes, which is a specific type of model-based classifiers. And again, we have different type of model-based classifier, but this naive Bayes is the most probably interesting one, and the type of model that is somehow related to what you have seen so far, perceptron and neural network, has a specific structure. So this Y is the variable that determines the label, and these FIs are variables that are associated to the features, right? And again, so these all of these variables are you can think about these as some sort of probability distributions, right? So this has the structure that we can reason about these connections, we can reason about each variable, and we can calculate these conditional probabilities, the joint probability distribution of the model, and many more, right? So now I have one question for you, that for those of you who know about BaseNet, why we want to have such a structure? Why, for example, we do not consider a structure like this, where the connections are the other way around? Why this structure makes more sense? And what is really bad about this structure? What is good about this structure? Can you give me some intuition?
Because we want to infuse conditional probability.
Okay, tell me more.
How do I explain this? If we use the upward pointing arrows, Y would depend on so many variables instead. But going from Y to other variables, I think it makes more sense and easier. So
can you tell me why it makes more sense? In what sense?
If Y depends on lots of variables, we need to determine all those variables F1 to Fn, which will be more work. But if those variables, some set of variables depend on just one variable, we only need to determine just that one variable.
Yeah, that's good. I like it. So let me clarify a little bit, right? So for example, if we want to calculate the joint probability of based on this structure, right? Based on the structure where, so what do we mean by joint probability? By joint probability, we mean, let me, whether I can open, right. So by joint probability, if we have such a structure, we want to calculate something like this: probability of y f1 all the way to fn. So this is a joint probability we want to have, right? So if we have this connection the other way around, by rules of probabilities, we know how to calculate this, right? How we calculate this? We start from the nodes without any parents, right? So we start from this f. So we say that probability of f1 multiplied by probability of f2 probability of fn, right? Multiplied by probability of what?
Y given all of those other
Exactly. Y given all of these, f1 all the way to fn, right? So we know that how large this probability distribution is.
2n plus 1.
Exactly. So this is too large. So if we have n variable already in the conditions, we have one variable here. So we have 2 over n. If these f and y only have 2 values each, like if we have 10 values, would be 10 over n. Okay. So if we assume they have 2 possible values, like 0 and 1, right, for all of them. Now, this is the total size of this table, right? What are the size of each of these? This is like 2, 2, 2, right? The whole thing, to calculate the whole thing, this is too much, right? Again, we have the curse of dimensionality. And again, for calculating this, this is no good. This structure didn't help us to save a space. We still have the curse of dimensionality. But if we have the other way around, so if we have this relationship the other way around, now this probability distribution of y, f1, and fn, this factorizes to something very simple. We start again by this node because it has no parents, p of y. We know what it is. It is very small, right? So it has a table with 2 rows, right? If it only has 2 values, right? Multiplied by probability of what? Probability of these guys, right? Given its parent. What is its parent? Probability of f1 is only y. It has only one parent, right? Probability of f1 given all of its parent, which is only one, y, right? Multiplied by probability of f2 given its parent, y again, multiplied by f, a probability of fn given y, right? So what we have seen here is that how large this probability distribution is. So this probability distribution is not really large, right? Has only how many values? Tell me. How large this is?
N plus 1.
Why n plus 1?
Well, there's the value of y, probability of y, and then multiplied by the probability of each of the individual conditional probabilities.
Right. So this is at most like we have like one variable if it has 2 values, right? This is also 2 values. This could get to 2 over 2, right? Sorry, 2 over 2. So this is really a small table, right? It is only dependent on two variables, right? So this factorizes into something very simple, right? We have a lot of simple structure. So if we have limited memory, like this is a lot better. So how much space do we need? Like we have n of these, right? So we have n 2/2, and we have 2, right? For this guy, right? So it is a lot simpler than this guy, right? For this guy, we needed to have a lot of space for storing this simple guy, right? So this structure, even though we assume something about the independence or dependence of different variables, it makes much more sense in terms of simplicity of the calculations that we need, right? And that's why we have such a structure in the model, and that's why it makes a lot more sense for doing so, right? Do you have any question about this?
Yeah, I was just wanting to make sure I understood. So the two for each of those conditional probabilities, that's referring to the 4 like combinations of the 4 possible, like these these are discrete variables. They can be on or off, I guess.
Yes, these are discrete variables. They can be on and off, right? That's correct, right?
So that's what you mean by the values, is there's 2 possible for each of them, and there's 2 for the conditional probabilities.
Exactly. So for example, y could be, like, you remember, for a spam and ham was like a spam ham, right? These could be like whether we have a loop or not, right? So discrete variables, right? I mean, like, it depends on the notion of each variable. So it could be 2 possible values or more, but still these are discrete variables. Right, and so for this, for having such a structure, you only really need to maintain this amount of parameters at the end, which is a lot more simpler than having a large model that we cannot keep track of. So that's why we want to have such a structure, and that is the reason why Naïve base is based on such a structure.
Could you elaborate on the meaning of the arrows?
The meaning of the arrows is the dependence between 2 variables. So this means that the y is dependent on f1, f2, and fn. So meaning that y is not, so in probabilistic sense, y is not independent, is so this is the notation that we have, like so if we have this notation, means that y and f1 are independent from each other. But here the presence of this means that these are dependent with each other. So we cannot have independencies between 2 variables. And in AR course, we discussed extensively, okay, how we can test about the independence from the data and so on. So there are some statistical tests you can do on the data to reason about this dependence. You could also have conditional independence, right? So you could reason that you may have independence between X and Y given some other variables, right? And we discuss about type of a structure that gives you this type of independencies between two or more number of variables. So for example, when we have X, then we have A, then we have Y. So we know that like this is by looking at this structure, we know that X and Y are really dependent, right? So because of this structure implies that X and Y are not independent, right? Because they are dependent through A, right? But if we know about A, so for example, if somebody tells us that A is like rainy today, right? It's if this is about the weather condition, right? Then we know that X and Y are independent, right?
That makes sense.
Yeah. So this is the implication of the structure of the model and what we know about the particular observation from the data, what we assume that we know about the data, and based on this knowledge about what we know, what we don't know, what we can assume, what is the structure of the model, we can reason, okay, whether we have independencies or not. So in this case, we can say that X and Y are independent given A, right?
Mm-hmm.
Because if we know about the A, then X and Y become independent. But if we don't know about anything about A, X and Y, we cannot say that these are independent, right? So that's a kind of reasoning we can have.
So would I be correct to say that the direction of the arrow, notionally at least, determines the relationship of cause and effect in a correlation? But what you're saying.
Yes, yeah, the direction matters. The type of a structure matters as well, right? So if you look at the details of Bayes nets, we have like a structure like common cause structure where we have A, X, and Y, right? We have V structure where we have X and Y, and then these are connected through A in this way. So we have different sort of a structure, and based on each of which, we can reason about the independence or the dependence between two variables, X and Y in this case, right? So for example, if we know about A in this case, then X and Y become independent. But in this structure is totally different. In this structure, we can say that X and Y are independent, but if we know about A, these two become dependent, right? So if we know about A, then there is no, so these X and Y become dependent. So different structure implies different dependencies between different variables. But we are not going to detail, like you can find much more information about Bayes nets in the AI course. This is beyond the topics of this course, but hopefully this gives you some intuition about this sort of models that we have.
Yeah, thank you.
Sure. Thanks for asking. So let's look at some more details about this type of model. So again, we have this kind of joint probability distribution, right? So these are feature values, and this is your label. So this joint probability distribution, you can think of, because these are specific values for these features. So more explicitly, you can think of Py F1 is equal to F1, right? And Fn is equal to Fn. So you know that like these are variables, these are specific values that is assigned. And that's why this is a kind of vector where for different values of y. So in this case, this is like, this is probability of y is equal y1, f1 is equal to f1, and so on, okay? And the same for the rest. So the goal is really to compute this posterior distribution over the label. What it means is that, so let's think, what do we expect from any classification, right? What needs to be learned here? What kind of probability we want to predict? Can anyone elaborate on that? What is the goal here? What do we want to get? We already discussed that before.
Conditional probabilities?
Exactly. What is that conditional probability? Can you specify?
Like the probability of y given f1, and then the probability of y given f2, and so
exactly.
on and so forth.
So the goal is to calculate this posterior probability distribution, and it means that we want to calculate probability of y, which is the label, given all of the feature values, right? Given f1, or better to say, given f1, fn, right? So this is the model we want to build. And once we have this conditional probability as a model, once we get a data, we can say that we can say that what is the probability of y is a spam given f1 is particular value for these features and fn is particular values for these features, and these are coming from your data, this data point that you give to the model, right? So this is your x. So in general, you want to have a conditional probability of y given x. This is the thing you want to construct, right? So that's the goal we want to get at. And that's why you might think, okay, if you think about like the perceptron, you remember how we constructed the person, and that's a nuance that I would like you to think about. And that's why I mentioned about this naive base. Again, this is yet another reason. distinguishing between discriminative models and generative models, right? So in discriminative models, like what we had for perceptron and neural network, you saw that like we had the data and we extracted these activations, right? We extracted these activations from the features that we had, right? And that was the discrimination between, so these activations provided the discrimination between what label we want to decide about this particular input, right? So we had a discriminative model that either based on the activation, so we had ZI, we looked at argmax of this ZI, and we decide, okay, what is the label we want to assign for this particular input, right? And that was like a specific label that we could assign to this model, right? Or we had this transformation to probabilities. There we could decide based on the probability distribution what label we want to assign. But here you saw that like the first step, you want to calculate this joint probability distribution. This joint probability distribution is a sort of generative model. So you can generate really data based on this type of model, this joint probability distribution, and that's why it is a different type of model rather than discriminative. These are more generative models, right? And then you know how to calculate each of these, right? So first, you need to calculate this joint probability distribution. How to do that? This is the way how to do that. You know from the structure, because Y's are dependent on these FIs, right? And then for each of these, we know that for this, for Y1, we can multiply our prior to these conditional probabilities. This is what we just discussed in the previous slide, right? So we calculate this, and then once we have these probabilities, we need to normalize them, right? So these probabilities, because is the multiplication of several probabilities, this vector doesn't add to one. So this is not a this vector is not a probability distribution. These are actually very small numbers because we multiply probabilities which are between 0 and 1, many of them. And you know that by the laws of numbers, if you multiply many numbers between 0 and 1, at the end what you get is a very small number, no matter what. How to do that? We know by calculus, right? If we if we add all of these, and if we normalize, basically dividing each of these entries based on the sum of all, then we get some probability distribution, right? So basically, this is the normal procedure, and then we have this discriminative model. So so we get this probability distribution because this is what we wanted to get or what we wanted to construct. So based on this normalization, we could construct this discriminative model or posterior distribution of over these label variables. Any question about this? Is this clear? if it's not, please ask, because that was the most important procedure you needed to know for this. So the mechanics of naive Bayes is really simple. You start with a bunch of probabilities, specifically these prior and these conditional probabilities. And then you do this inference for computing this conditional probability, this discriminative model. Right. So we discussed about this. So let's have some example for digits. What is this prior? This is your prior, right? Typically, P of Y, this is what you call prior, and the reason why you call it prior because this is the probability distribution over your label data, and this is coming from your data really. So, and this means that prior means that what. So let's clarify what is prior. Prior means that what is your belief or assumption about what is probable or what is not before even looking at any data point, right? So imagine that you are given no data point, right? Imagine that you came into the world, right? And you have zero experience, okay? So with zero experience, like you have no experience, meaning that it really depends on how much you want to trust others, right? So this is like about your prior or beliefs, some unknowns, right? So if you want to distinguish between a bad person or good person, this is your prior. Some people are pessimistic, meaning that they assume everyone is bad unless the otherwise is proven. Other people, they assume that everyone is good unless basically the other way around was shown, right? So this is what we call prior, and typically for many of these machine learning models, we start by uniform prior. We assume that all of these digits are the same probable. So you start off by this uniform distribution, and this is again, for your prior, you need to have a probability distribution. And that means that if you sum all of them, they have to sum to 1. And then we have these conditional probabilities. What are these conditional probabilities? Means that, for example, what is the value of F3, 1? This is the third row, 1, right? So this is 0, 0, 1, 1, 2, 3. Okay. So what is the pixel value of this? So it means that what is the probability of this pixel value is on given a particular label, right? So this pixel value, we knew that we assume this structure, okay? So if we have this, we need to look at all possible values of y. So if this is on, what is this conditional probability? So for label 1, with this probability 0.01, it is on. With 0.099, this is off, right? So when you have this situation on and off, you only need to know about one of those, right? And you can deduce the other one. And this is more probable, 5 times more probable for 2, and a lot more probable for 5, right? So because for 5, you have something like this, and that's why this is most of the cases. This is on for 5 and for 6 as well, right? So you see this conditional probability, how you need to make sense out of it. You have the similar conditional probability for other features, right? For F5 and 5, and so on. And then once you have these data, these little structures, and again, you saw that these are little structures. These are not large table. Because of this structure, we made them small. Then you can calculate this generative model. You only multiply P of Y to these conditional probabilities, right? And then you get this generative model, and then you do the same procedure as you know. You can do the same for text as well, right? For the text, you can look at, okay, what is the word, a specific word in a specific position in the text, and that's how the features looks like. But again, nothing unusual here. They are more or less the same. Again, let's go through one example. This is the your prior assume that 2/3 of your emails are probably benign, 1/3 might be a spam, and then you have this conditional probability, meaning that given P of W, if the W is D, given it is a spam, what is this probability? And the same for ham. So you have these sort of tables. This is these entities because you need them to construct this joint probability distribution. And obviously these tables come from your data, right? So you have a corpus of data, and you can construct this conditional probability based on your data. And you start by your prior. Prior tells that, right, without, so this is really without seeing any data, this is what you can rely on. Most probably, this is going to be a benign text rather than a ham. And then you see one word in your text, Gary, for example. Gary, so this means that probability of Gary, if this is a spam, is this probable, and is a lot more probable if this is a ham, because it's a particular name and it is your name, and then this is the probability distribution. So far, meaning that given that we only saw one word, Gary, this is what the model thinks. The model thinks that this is a ham. And then you see another word, would, based on your conditional probability. This is more probable, slightly more probable. This is ham. Again, your model thinks that this is a ham given this data. And then you see you, this is a lot more probable to be a spam. And then you incorporate this conditional probability to your generative model. Still, your generative model thinks that this is going to be ham, given your model has seen 3 words. And then as you observe more data, this probability distribution would change. And note that these probability distribution, these are after transforming to log probabilities, right? That's why you see. So if you remember, log would looks like something like this, right? And log transformation would be helpful if you have a small probabilities, so you can distinguish them better. As you observe these words, you see that the model thinks that still at this point thinks that still is a ham. Still after seeing glues, still thinks that it is a ham, but you saw that it's getting closer to each other, right? And at this point, when it saw weights, it minds that this is going to be a spam probably. And then you are asleep, and at the end you saw that this is a lot larger than this one. So in log, so this is more probable as a true label for this particular example. Does it make sense?
Actually, I'm just a tiny bit confused. Why do they use negative numbers to quantify whether I think it's spam or ham?
As I mentioned, these are log transformations, right? So if you have a small probabilities, after you log transform the probabilities, log p, right? So you so basically your numbers, right, lies here. So you're talking about negative numbers. Does it make sense now?
Yeah, that makes more sense.
So basically, these are again is a mathematical trick. When you're having a small probability numbers, it is a trick to transform them to log probabilities rather than just probabilities. There are some computational reason because this probability gets a small. Most probable it is the case that your computation would underflow, so you don't have the capacity to represent very small number in some computers, and that's why you want to transform them into log probabilities, because obviously you can represent these minus number rather than like something like 0.00000000001, right? This has a chance to be overflown, but not this. And that's why you typically transform them to log probabilities. These are simply just some transformation, but some mathematical.
Yeah, I get it now. It's pretty simple.
And then at the end, you calculate what is the probability of a spam given like this particular words, right? And then you calculate back all of them to probabilities, and you get this probability value that with 98.9% this is a spam, and with 1.1% is a ham. So that was all about this type of generative model, this type of classifier or model-based classifiers, which again, I would like to emphasize that this is a probabilistic model. So you had a structure and you learned about the parameters of your variables, this structure, and then this basically gave you give you this reason why you want to and what kind of difference you see between this type of model and some model like non-probabilistic version of this in what you have seen in neural network or perceptron. So there are some details about like empirical risk minimization and what is the best model based on your training data. We discuss about some of these and what is overfitting, what is hypothesis space, what is regularization. These are again some of which we discussed, but let's also maybe have some conversation about this, right? Because these are again important, right? What do we mean by generalization? What do we mean by overfitting? Overfitting is really simple concept, but yet very important concept in machine learning, right? If this is, for example, your data, like one may say that, okay, I want to fit the best model in the data, and like one may try polynomial of degree 5, but one may say, why not a simpler model like a linear model, right? This is a lot simpler model than this polynomial, even though the empirical risk minimization based only on your training data would prefer this model over this, but the simplicity of this linear model is appealing when you want to get a better generalization. And actually this would happen in practice in several different contexts, right? So you might have heard about the simplicity of a model and generalization. Typically, we know that simpler model would generalize better, and that is basically pretty much a intuitive notion as you see here. Another type of overfitting is specifically for this type of model-based classifiers, where really you only rely on data to estimate this conditional or probability distribution, right? We discussed where these conditional probability or prior come from, your data. If you do not have any data that represent one of these features, then your probability becomes 0, and that's bad, right? So for example, in this case, like if you only rely on your data, the probability of this pixel is on right is 80%, right? For example 2, for example 3 is also 80%. For this case, for this particular pixel, for example 2 is very different probability from example 3, but for something like this, for example 2 is also different. Well, maybe you have some cases that the probability of one of these pixels for particular example is really 0. You do not have any example in your data that this pixel is on for label 3, right? For none of your example, this pixel is on. So what you can infer from data is maybe this probability is 0, right? So this conditional probability is 0. And then in this case, right, so if you look at this, right, so if you look at what would happen, so far, like up until here, before you see the last one, right? Before you see the last one, 3 was much more probable, right? Here so far was equal, here it was equal, here it becomes much more probable. For this case also become much more probable. So far 3 was winning, but only because one of these was 0. This was also very small, but not 0. This make it 0 probable because you multiply these together, right? So everything was turned the other way around as a result of this value become really 0 instead of a 0.00001, right? And that is called, again, overfitting. There are some solutions for this. So this probability becomes messed up. If some of these are 0, then these are infinite. And these techniques, like there are some techniques for smoothing and regularization, which later on we will discuss in more detail. But in order to, what time is it? Maybe let's stop here. We discuss this in detail later on, because maybe it requires more example to discuss. But typically these are some techniques that enable you to reason and select the parameters of your model that gives us better generalization power. And while it's still simple, and also avoid such problem of overfitting as well. So let's stop here, and we'll talk to you next week. Thanks.
Thank you.
Thank you.
Thank you, Professor. Have a good day.
You too.